Okay, thanks. Good afternoon, everyone. Just give you a quick outline of what I'm planning to be talking about. I have a quick introduction. As Jennifer said, I've been looking at Scour monitoring techniques that are being worked on in CSIC in the Langer Rourke Centre, and looking at the ways that we manage Scour risk to mainly bridges, and then see the applicability of some of these new monitoring techniques. Just a little bit about me to start with. I studied my engineering master's degree at Cambridge back in 2006 and followed that with a PhD with Cam Middleton looking at structural health monitoring of bridges. After that, I joined Parsons Brinkhoff, which has now become part of WSP. I've been working in their bridges team since then on a whole range of projects, from sort of design of small scale structures to kind of wider schemes, working with Highways England and Network Rail, looking at how they manage their whole stocks of bridges and what they should be doing around the most efficient way to spend their maintenance budgets. The aims of this secondment were really to look at some of the emerging Scour monitoring techniques that are being developed here at Cambridge, and then try and draw on my experiences of using monitoring systems and working with asset managers to identify some of the potential benefits and limitations of those for asset owners, and to try to pull some of that together into some practical guidance. So just a quick sort of revision session, if you like, to start with. What is Scour? Scour can be described as the removal of material from the bed and banks of a channel and from around structure foundations by the action of water. So it's a natural phenomenon. Basically, as water flows along a water course, sediment gets transported from one place to the other. Depending on the speed of the flow and the size of the particles, you might get some areas where the bed level goes down. If this happens around the foundations of your structure, this can cause problems, so the foundation loses support, and in the worst case, leading to partial or total collapse of the structures. Why does it matter? And this is, I've stolen this slide from Kaysen, but this is a study that he'd dug out, which has been carried out in the US in the 1990s, where they looked at the causes of about 500 bridge failures, and Scour is the single biggest cause of bridge collapses from that study, and the very similar story in the UK. It's one of the major causes of failure of structures, so it's a real concern for asset managers. So what do they do about Scour risk at the moment? There's a whole variety of guidance available at the moment, and Scour is a relatively well-known problem. So for new structures, it's generally not too much of an issue. It gets taken into account during the design, and the structures can be designed with suitably deep foundations or protection measures to protect against Scour. But for existing structures, there's guidance that Highways England publish in BD 97, which is their document about requirements for the assessment and management of Scour risk. Network Rail have a very similar suite of guidance, and there's guidance produced by Syria as well covering this. Broadly, these all set out the same sort of process, and it's really about identifying risk of structures which could be affected by Scour in your stock of structures, and then finding ways to manage those risks. And the various different guidance documents broadly break these down into the same 4 sort of steps. Starting at the top with anticipate stage, which is a sort of course screening, which is aimed at eliminating structures that are not Scour susceptible, really. And this is using sort of easily available information, things like, is the structure near a river or not? And if it's nowhere near a watercourse or it's founded on solid rock, it's going to be very low risk and kind of be pushed away from the ones you're looking at. Next comes an assessment phase, which is typically where we try and calculate the expected Scour depth under a design approach, using some simplified approaches, but needing some more information about the flow characteristics of the particular watercourse and the soil properties. And you can compare that expected depth with the depth of the structure's foundation and end up with a numerical risk rating, which allows you to rank the structures you've got in order from sort of highest risk to lowest risk. Then moving on to what we can do around those risks, there's sort of preventative actions, which is where we we'll talk about a bit later, taking actions to manage those risks, and preparing where they need to put together plans for responding to scour events if they happen, and implementing any sort of emergency actions. And then this whole process gets repeated on a cycle, because things change over time. So there's a process to go through reassessing structures to make sure things haven't changed and make sure that any new risks are still picked up. The sorts of preventative measures that can be implemented can be things like doing further investigation, doing some more detailed analyses, implementing monitoring measures to try and measure the amount of scour that is occurring, or to provide warning if things are getting worse, and protective measures to make bridges less vulnerable to scour, which could be constructing sort of aprons around foundations to prevent scour development in localized areas, or changing the shape of piers, things like that. Some of the key challenges at the moment: scour is quite difficult to accurately predict, as well as being quite a complex thing to try and model. You never know if or when a flood event is going to happen, and most scour tends to happen during flood events where you've got a much increased water flow, so there's much more erosion of the riverbed goes on. And most of the monitoring equipment that's commonly available to try and detect this happening tends to need to be installed under the water level to look for changes in the riverbed level, and so it's very susceptible to damage from water, damage from debris flowing down the river during floods. So what I've been looking at during my time here at CSIC is a couple of new monitoring techniques. The two I'm going to talk about are satellite-based techniques, which is based on work that Sakthi's been doing through her PhD and carrying on with, and some vibration techniques, which Payson has been working on. So to give a very basic overview of how satellite-based techniques work. This uses radar systems which are mounted on satellites orbiting around the Earth. So the radar beam kind of illuminates the Earth's surface as the satellite orbits past. Reflections from that can then be detected by the sensor on the satellite, and each pixel in your image represents the magnitude of the signal that's reflected back. So you get an image that looks something like this, and the magnitude of the image that comes back depends on the distance between the satellite and the thing on the ground, and the reflective characteristics of what's reflecting. And you can see in a picture like this, sort of hard objects which show up brightly tend to reflect radar waves quite well. Softer things such as water don't. So you can often pick up bridges relatively clearly. This is a picture of London. You can see the bridges over the river, because the water in the river doesn't reflect radar waves very well, and the bridges do. But by itself, this is not particularly useful, because unless you know exactly what the reflective characteristics are of each pixel, you can't work out anything about the distance. But if you take a second picture at a different time and compare the two, one very useful feature is that you can look at the phase shift of the wave that comes back, and the difference between your two images. And if there's been any small movement of the object you're looking at, the reflected wave has a different phase relative to the wave that went out, and that's directly proportional to the change in distance. A case study that Sakthi looked at was a bridge in Tadcaster in Yorkshire, which in December 2015 partially collapsed during a flood. And this is a plot of the distance measured to various points on the bridge from a satellite over the months running up to the period of collapse. These green lines are a measure of kind of outliers. So she was trying to detect what's happening with the structure. It's sort of moving around a little bit, and then shortly before it collapsed, we can see a large vertical displacement, which was one of the piers starting to settle before the structure collapsed. So this kind of demonstrates the viability of picking up small movements from these satellite measurements. There's some really interesting potential benefits of this technique. One is that there's a very wide coverage area. Imagery is available anywhere in the world, and you can take really large images, so you can potentially include hundreds of structures within one image, which for an asset owner with like someone like Highways England, who've got thousands of structures, I think that's a really interesting potential where they can potentially monitor lots of structures in one image and pick up sort of areas where movement might be taking place. It's also a good archive of historic imagery available, which means you can go back and go back and look back in time if you identify areas where you might have a concern. And in most cases, you don't need to do anything on site, which has a huge benefit for health and safety risks of working on site, because most structures naturally reflect well enough. And if they don't, it's relatively easy to install something like this, say an aluminium reflector, which gives you a much stronger reflection. There are some limitations, though. I'm going to run through these quite quickly because of time, but you clearly need to have a direct line of sight between the satellite and the thing you're monitoring. So if anything gets in the way, like vegetation or tall buildings, your satellite just won't be able to see the structure. So it's not going to be suitable for everything. If anything changes about the structure, so the reflective characteristics change, it's then very difficult to work out that you're looking at the same thing. So if your structure gets resurfaced, you can kind of lose your datum point. It's also only a one-dimensional measurement. It's the distance between the satellite and the structure. So if there are movements if you're sure the movements are only happening in a vertical direction, that's fine. If your structure could also be moving longitudinally, there's a potential of uncertainty in resolving the measurements there. If the movements are too large, you can't tell the difference between a shift of one on whole wavelength or 2 or 3 or any number. So the technique only works for picking up small movements that happen relatively slowly. And then another limitation is the measurement frequency. The satellites are orbiting and typically only return to the same place about once every sort of 5 to 10 days. So if you're so you can only obtain data at that sort of frequency. Second technique is looking at the vibrational characteristics of structures. And the basic principle of this is that if scour occurs around the foundations of a structure, like in this picture, the stiffness of this pier is going to change, and so there'll be a change in the vibrational response of this structure. You can either apply a known force and measure the response, which is typically quite difficult to do, or you can measure the ambient vibrational response and extract natural frequencies and mode shapes from that. And although the natural frequencies predicted to change, work that Kaysen was looking at through his PhD found that the effect's really quite small compared to the uncertainty in your measurement, but changes in other properties like the mode shape of vibration of the columns and the power spectral density related to that are much, much more significant. And this is a case study of a bridge in Bradford in 2018, which had suffered some scour damage, which was being repaired. So they had the opportunity to install accelerometers at places on the piers of this structure and see what happens sort of in reverse as some repair works were undertaken. This is a scan of the riverbed. The grey line shows the riverbed level at the start, where there was about a 1.8 metre deep scour hole near to one of these piers. That was then filled in during these remedial works whilst this bridge was being monitored. And this is a plot showing the mean power spectral density of horizontal vibration at that middle pier. And for one of the vibration modes, there's a really clear reduction in that power spectral density as the repair progressed. So it's, again, showing that
2 minutes.
Sure, okay, thanks. There's a clear trend that we can spot here in detecting the differences that scour is causing. This technique's very easy to install. There's plenty of existing suppliers who can install accelerometers. It's much less susceptible to damage than the traditional monitoring techniques, as it's all installed above the waterline. And I think another benefit is you're directly measuring the structure. Most scour techniques tend to try and detect the change in the depth of the riverbed, and then there's another sort of modelling step to relate that to the structure. Again, it's not going to be suitable for all structures. You need to be able to detect changes in the vibrational response. So it works very well for bridges with slender piers, but not so well if you've got sort of large masonry structures. And it can be tricky, I think, to relate the the changes in vibrational response to an actual scour depth. So although you can tell that there is a change, sort of setting a threshold beyond which you've got a problem is not always straightforward. Just to wrap up, and I've only got a few seconds left, but I think there's a general view that monitoring systems have limitations for use in scour detection, and there's several bits of guidance state that protection works are considered more reliable than monitoring as a way of managing the problem. But this means you often end up with potentially unnecessary works, which are a cost to asset managers. So I think some of these new techniques, there's no one size fits all, and these could form a part of a sort of toolbox of techniques available to asset managements. And deciding which one is the right technique to use, I think it's really important that we are clear on what the purpose of the monitoring is to be. And sort of two areas where these techniques are, I think, have particular potential are in sort of once you've identified a risk of scour, monitoring its ongoing development. So identify whether we need to do anything more urgently or whether we can still safely use the bridge before doing that. And the satellite monitoring in particular, in sort of because of its wide coverage in these kind of those uses of identifying areas of risk and kind of improving that periodic reassessment approach rather than just doing everything on a time-based approach. I think we could be much more sensible in doing that. I'll wrap up there. Sorry, I've overrun very slightly, but I'd be happy for any questions.